Okay, well, everybody can hear me. All right. So the sequence of these two lectures have been really well organized, because I'm going to be speaking exactly about declarative concurrency and this language called Ozma. Right. So first of all, I want to extend my thanks to the staff of the organizers. It's been great coming out here. I'm from Hong Kong. And yeah, it's been quite an interesting time getting here. 32 hours of flight to get here. I mean, of traveling just to get here. All right, so I'm bucking the trend a bit. I'm not going to have any slides. I want to avoid this. I prefer a more engaging kind of audience. So, you know, conversation. You can throw questions at me. Not too much. Don't derail me too much. Huh? I'm still a new speaker, so I'm trying. Right. Now, we're going to start off by extending thanks towards Peter van Rooij and Sebastian Doreen, who are the real brains behind this. Peter and Sebastian are from Belgium, from the University de Leuven, and they're the main guys behind this programming language called Oz, Mozart Oz. I don't know if any of you are familiar with that. Who here is familiar with Mozart Oz? One person in the room. That's because I told you. Yeah. All right. Okay. So. All right. Who here is familiar with the book called Concepts, Techniques, and Models of Computer Programming? Right. Okay. So if you're at all into concurrency, dataflow, anything like that, I really, really recommend you buy this book and read through it. Okay, it's a bit of a thick one though, but you can go through it. All right. Okay. So I was thinking about how I'm going to actually start this talk off, and I was thinking of that, because how I'm going to introduce is by saying I am water, and I thought, well, that's a bit strange to do this, but actually it ties in quite well, because when I say I am water, I'm actually referring to the intrinsic nature of water, which is the H2O. And we can look at, there are different kinds of waters, for example, seawater, tap water, and rainwater. They're all different in nature. They all have different makeups. But if we get fixated on these differences, then we start to kind of like have a judgmental heart. And this causes us to be a little bit uncomfortable when we reach certain situations, make certain decisions about things regarding water. But if we rather focus on the intrinsic nature of water, then what happens is we see all water as the same. So us as technologists, we are technologists. We're not groovy programmers or Java programmers or anything. We're all in our own ways, we're pushing ones and zeros. So from this point of view, I hope we can try to throw away those old mindsets of different languages and whatnot, and rather focus on more the intrinsic nature of our technologies. Start off by drawing a line. Paradigm. These are languages. So there are multiple languages. Hodgepodge, and maybe one or two would implement a few paradigms. And then there are concepts. Concepts are well organized, well thought out, and maybe a paradigm would implement one or two concepts. I'm going to steal somebody else's water. Now, so what many of us are doing, we're fixating on languages. We're saying, I'm this person, I'm that person. But we're not actually able to kind of go down and actually analyze and study the concepts of what make up a language. Doing that would be most beneficial for us. In other words, we're focusing on the intrinsic nature of languages. So, as this is H2O, the intrinsic nature of water, so this is the intrinsic nature of languages. And we no longer have to identify, I'm a Haskell program or something like that. We can see them all as one. All right. So, and what I'm going to do now is I'm going to re-implement a declarative programming language from scratch. So we're going to work from basic foundations. We're going to build layer by layer using a concept, this technique called the creative extension principle. Now, the creative extension principle is where we're using a medium of communication, which would be our language, our computer programming language, and as soon as that becomes more complicated, when we're having more problems implementing the problem, we're getting more problems from the actual language than from the actual problem that we're trying to implement. That means our language is ripe ready for a new concept to be introduced into our language to make it a lot easier for us to be able to solve this problem. So a very good example, probably the canonical example of this creative extension principle, is if we have a language like C, for example, and we have an error in C, what will happen to that program? It will crash, right? So we have to make use of these error codes which flow into and out of these functions, right? We're all familiar with that, right? Who hasn't used error codes before? Right. Okay, so you would notice that as you're using error codes, the complexity of the error codes actually spread out in a global fashion throughout your program. And it becomes a little bit more difficult to maintain that complexity. So what would be a very good concept to introduce to this programming language to reduce the complexity? Any ideas? An exception. Exactly that. That reduces the complexity of your global error messages down into maybe 1 or 2 lines at the bottom of a function. There's an example of reducing complexity by introducing the right level of extraction at the right time. So, in order to build up this declarative concurrent language, let's start off with a foundation language. What would be a sensible way to go? Any ideas? Just a simple, basic functional language. Just start off with that. It's very good. It's a lexically scoped closures, so we can actually each function will be able to fit into our mind, and we can layer them and build them up into a structure. It's quite a powerful concept, quite a powerful structuring technique in writing programs. So we'll start with that point. And the next thing but it's still not expressive enough. We still need to introduce something else, which would be those functional tools, which would be like map and fold. Stuff like that, tools like that. We need to use things like that. And of course, we need our symbolic data structures, which would be lists, numbers, atoms, and records. Records are basically key value data structures, which make things a little bit easier to do. Now we can actually start working with data. We can start do some programming exercises with it. All right. After this point, a good thing to use, a good concept to introduce into this language would be pattern matching. Another name for that is called unification. Unification, there are 2 kinds of unification. One is full unification, and another one is shallow unification. So full unification basically has, we have a data structure on one side, and you have another data structure on another side, and you have an equals in between, and what happens is the unification just makes both of those data structures equal. So the equal sign will dig into the data structure and then make them all equal to each other. That's called full unification. Shallow unification just makes a value-to-value unification. So we're starting to build up a more powerful technique. Those of you using Erlang and other languages, you're quite familiar with pattern matching and how powerful it is within when you're programming. All right. Next, after pattern matching, introducing pattern matching allows us to create selective receives, which we will introduce a little bit later. Selective receives are available in programming languages like Erlang. And those of you who know Ulf Wigge, who is quite a heavyweight in the Erlang community, he did a talk out there on the internet called Death by Complexity, I think, where he implemented a plain old telephone system using Erlang, using the selective receive technique, pattern matching, selective receive, and then he redid it using an event-based approach also in Erlang, but from that point of view. And then last of all, there was a case study using a language like C to implement the POTS network. And you could see that's the truth table of the pattern matching one. All of the conditions were perfectly within range. You could lift the handset of the telephone, put it down, dial a few numbers here and there, and everything would happen in sequence and all predictable. Yet when you moved over into the event-based mechanism, you'd find certain scenarios, states would happen, which would cause the program to crash and have a few issues. And then, if you, making reference to the third one, the C-based implementation, the documentation was just so long. It was so complicated that there were so many different states and conditions that could happen, and that the whole thing could just fall apart. So making use of selective receive is a very good way of handling and reducing complexity within your program. Okay, after pattern matching, a good thing to introduce is higher order programming. Higher order programming just means that you have a function's arguments or return value can be another function. So this allows one to make use of a powerful technique to have functions which write other functions. Now we get to the meat of the matter, the data flow concept. Data flow, this is the second reason why I introduced by saying I am water, because data flow is in essence a kind of way of looking at how water how water can flow down a mountain. So you could have, for example, a series of channels with like you could say buckets along the way, and then as the water flows down, it fills up and then moves on, and it fills up and it moves on. Very simple way. It's all deterministic at this stage. So how do we implement data flow in this language? First of all, we need to have immutable variables. So they either exist in two states, either unbound or bound. And when they are bound, they cannot be changed. So they're monotonic. Okay. This allows us to be able to perform a series we're not at the point where we can do calculations yet, because if we have x plus y is equal to z, and we just have the value for y, what's going to happen is that it's going to block. Your code is going to block. It's just going to stop. And whenever you program in a data flow paradigm, and you see a section of your code just stopping, that's your indication that there's a bug in that section of the code and things are not working accordingly. So what we're going to do now is we're going to introduce concurrency into this matter. Now, what is concurrency? This is important because in the talk before us, there was seemed like a confusion between parallelism and concurrency. So concurrency just means that you can have more than one task happening pretty much at the same time. That's all concurrency means. And having good concurrency allows you to have good parallelism. So how do we implement concurrency in this language? In a data flow language, it's very important that you have one of two types of concurrency. One, you get competitive concurrency. Another one, you get cooperative concurrency. Now, competitive concurrency exists in the form of these operating system threads, where a thread will try to consume as much processing power as possible, and this can lead to thread starvation of other threads in the system. Now, would you agree that having thread starvation in a data flow programming language is a definite no-no? Sure. You can actually lock up your entire system by having thread starvation. So an example of thread starvation is if you go to the bank and you have your premier queue, the business queue, and then you have your ordinary queue, and you've only got one teller. And this one teller is only sitting at the business queue, seeing to all of the business needs. So all of the normal customers, they just can't they don't have time with the teller. So that's an example of how we can actually create thread starvation and how it can actually destroy your programming language. So I'm going to go a little bit deeper. I don't know if I'm probably getting a bit too technical here, but you let me know. How to implement a cooperative concurrency in the system. We basically need to have 3 queues. 3 queues of different priority. This would be low, medium, and you'd have high. And these queues are basically hold the threads that we're going to create, because the language construct of this concurrency that we're going to have is just a simple keyword. The simple keyword is just thread. Now, thread have different priorities. You'd have, for example, VM-specific threads would be put onto the high priority queue, and your normal programming language threads would be probably put onto the medium priority queue. Now, what would happen is you'd have time slices, and time slices basically uses a hardware interrupt to allocate processor time according to each queue. So, as a thread, a dataflow thread, is ready to do computation. In other words, all of the variables have been met and they're ready to go on. Then that thread will then be put into whatever queue it's associated with. And then as the processor time comes up, its next turn, it will consume those threads and process those threads in that time segment, that time interval. So that's a way to implement cooperative concurrency in this data flow, because we actually have to have that. Right. After we've got data flow and how to implement concurrency, these two concepts, just data flow and concurrency, allows us to start doing data flow computation. Data flow computation basically means that we can take, for example, we can create 2 threads, and on both of those threads we can put data flow variables, and as soon as they are met, they actually can communicate with each other, so that the 2 different stacks can communicate values across, which allows us to do data flow computation. This is great. It's like having 2 lines of people. So you've got 2 lines of people over here, and then person A has a ball. As soon as they finish their computation, they throw it across the way and give it to the next person. They take it and then throw it across the way. So you can see how data can flow across the two stacks. But okay, we've talked about that. But we need to understand that there are probably better ways of communicating between the two threads or the groups of people, and that's by using streams. So, what is a stream? What is a stream? A stream is just a list where the final element of that list is unbound. That's just a stream. And all of these elements of this list are data flow elements. So they're like potholes. So I can send a stream over to somebody over there and say, okay, you've got all these things that are a few elements in that stream which are unbound, but don't worry, my guys are working on it, and as soon as they've done it, they'll throw the ball into that element over there, which will fill up your stream or your list as it's done. So this is now we're starting to build up how to communicate between 2 different threads. But this is supply-driven. Supply-driven, so for example, if I've got one room filled with people working on a certain task, and we've got another room across the way and another group of people working on a certain task, and we drill a hole through here with a pipe, and as soon as the work units are done, we start pushing the balls through this pipe into the next room. Basically, what's happening is we're doing a supply-driven. As soon as we're done, we push these through. And it's gonna make the guys on the other end. They're gonna say, okay, wait, all right, slow down a bit. Just what I'm doing, what you're asking me to do is quite intensive. So you're creating a lockstep between producer and consumer. How do we solve that problem? Any ideas? That's exactly it. Demand driven. So what happens is we're all lazy. Everybody in this room is lazy. and then we hear a call coming through saying, hey, I need the next one. So we get working using our data flow, and then we pop the ball through, and then continue from there. That demand-driven execution allows the producer and consumer to decouple, which is great when you need to start putting for example, if this room is not next door, it is indeed on the other side of the world, we need to have a decoupling of agents. So you introduce the concept of laziness at this stage, which just means wait needed. And that allows us to do demand-driven execution. So up until now, up until the point of where I introduced threads, that's called declarative concurrency. It's a very good paradigm to actually to solve quite a lot of concurrent problems. It allows you to fit pretty complicated concurrency problems into your head without it exploding. It's a very sane way of handling these problems. Now, introducing laziness allows us to have this demand-driven programming, and then after that, we're going to allow us to create something called agents. Now, agents are things which are like the actor model. Basically, we're fusing the actor model with this declarative concurrent model. We're introducing a concept called ports. Ports allow us to bring non-determinism into the scene. So far, everything we've done is completely deterministic. And this programming language, being completely deterministic, it doesn't really work well with a non-deterministic world. So any program, you need to be able to have non-determinism in order for your programming language to interact with the outside world. So how do we do that? How do we constrain and cordon off the non-determinism of our program in a place which is safe, in a place which does not pollute the rest of our programming language? It's actually good programming in a deterministic fashion. It allows one to see very clearly and have the expectation that whatever we're going to calculate with this input will have that output. It makes life sane. So it's good dealing with a deterministic program. But how do we introduce non-determinism? The concept of a port is using these streams. Recall I mentioned we have streams of data being passed between the two rooms. Now we can have, for example, one agent over here which has one stream. This would be a port, and every port has a stream associated with it. So we would have a stream over here, but this stream can be written to by multiple producers. So multiple agents can write onto this stream. So if I were to write, so if we were to put, for example, thread, and we were to put maybe, okay, so this would be stream 1, and we were to put on the value 1, and the value 2, and the value 3. What would be the order that agent A receives? What would be the order that agent A receives this? Would it be 1, 2, and 3? It's non-deterministic. That's how we introduce non-determinism into our. I'm standing over here. The camera is facing over there.
Yeah, that's what you get for not using slides.
Right. Okay. Right. Okay. So here we've got non-determinism into this scenario. So far, this port mechanism does not form part of the declarative concurrent programming paradigm. It's just an extension of that. This has been around for about 20 years. This kind of programming technique. It's been around for 20 years. Why don't we know about this? Why don't we know about this? More and more people are speaking about declarative concurrency. This is now the third lecture where it's mentioned, declarative concurrency. So I see one person over there, dude, this is like really important. There are so many heavyweight academics who have been putting their knowledge and time into this paradigm of programming, and it'll just make your life so much easier. So what Peter van Rooij and Sebastian Dorian have actually done is they've actually taken the Scala programming language and they've extended it. They've extended Scala such that it has exactly what I was describing there, having this deterministic, declarative determinism with laziness and the porting mechanism, and they've introduced it into the Scala programming language. This allows you to use Scala's functional and object-oriented paradigm and also introduce concurrency on a language level. Having data flow and the mechanisms on a library level can be seen as cargo cult programming. Right, good, I got one nod at least. It can be seen as cargo cult programming. Because what happened is you using a foundation of programming, thinking, data flow is a cool idea. You know, some other guys are doing, let's go implement a library and put it on top. It's not going to work. Yeah, sure, you'll get some benefits, but the complexity of trying to integrate those two paradigms of programming is going to make your life easier. Just a moment ago, I was sitting in on GPARS, and I looked at this, and yeah, I can see that the understanding of declarative concurrency is entering into the mainstream at the moment. But it could be so much more simpler. But because it's using a library mechanism, it's quite difficult to actually see how to do it in a very intuitive way. So you can actually, I'd like you to go onto GitHub, you can write it down and then search for the keyword Ozma. And there you'll see a full implementation of Ozma. Ozma is it has a new backend. Ozma makes use of the Mozart Oz virtual machine. It has a new backend, and also it's extended this stuff, these concepts which I've spoken about. Now Sebastian's done a stunning job on giving a certain tutorials going into how to program in this technique. You can go over it. You can download the source code. You can get it running, and those parts of the Scala programming language which are running on those parts of Ozma are using the exact same compiler as the Scala compiler. So you can be sure that a lot of the semantics will remain the same. So you can try it out. Now, okay, so are there any questions so far regarding this? No? Okay, all right. So what I'd like to do is I'd like to start speaking a little bit more about the Oz programming language and some of the features of Oz. And as you guys don't know much about Oz, you said earlier, but Oz is a multi-paradigm programming language. It supports multiple paradigms. For example, have you guys heard of the logical programming paradigm? Yeah? Okay, one person. So we got object-oriented, we got logical, we've got constraint programming. There's a whole series of paradigms. These academics have spent time going into researching all of these different fields and bring them into this language. It's a great way to learn more about your field. So download Mozart, take a look at it, and see how it goes. Any ideas? Any questions so far?
About Mozart Oz and the Ozma project, which you talked about, which is Scala. Is the plan the two will coexist and follow each other, or is
no.
How are they related?
Okay, so Ozma, the intention behind Ozma is to basically show to the world, the programming world, this idea, this approach of doing declarative concurrency. It's meant to be an example, drawing from the wisdom of what has been learned from the Mozart Oz paradigm and bringing it into a language which is more available to the world at the moment. So Scala is possibly the most likely language to hit mainstream, and this will be probably the first real mainstream functional programming language out there, and that's the main impetus behind it. So we can go into, for example, more details about the actual implementation, but really I think it's a better way for you guys to actually go and read through it. It can get pretty intense, pretty technically oriented. So, for example, you would have exactly the same concepts of thread, but just all in the Scala all in the Scala syntax. Yeah.
So, is anyone, I know it's quite new, when I spoke to you in Hong Kong about it, it was it just come out and give it a day. Has anyone, apart from the author, done any big things with it yet? Is there any
No, I mean,
test cases or demonstrations?
Yeah, okay, so he's re-implemented, there was a particular example as a university and a project to demonstrate the flexibility and the expressiveness of Ozma. And that has been re-implemented, just to demonstrate, yes, it can be done. But actually going out there and using Scala to implement large-scale projects, I don't think that's a good idea. You probably want to use a more engineering standard of doing things. But it's not a wise thing. Sorry?
There are plenty of people like these in Scala, and it seems to tip over in some places. Really, do they know about this?
So this is basically this is the So this is the reason why I want to speak about this, to actually bring this into the mind share it with you guys. And so a lot of work has gone into it, and yeah, it's a good direction. Let's speak a little bit more about Oz. So the different paradigms, programming paradigms, are just levels of abstraction. Every problem has their level of abstraction, and which best solves that issue. For example, constraint programming. If you've got a search problem, you make use of constraint programming, and you illustrate those constraints that are needed to solve that problem. You just tell it to the virtual machine, and it heads out there and it just builds an entire search tree for it and gives you the answer. Now you can tell it in certain ways. Those of you who are familiar with constraint programming? Only one person. Okay, a little bit. All right. Okay. Is this talk is it gone straight over everybody's heads? Right. Good. All right. Okay. Right. So constraint programming, like for example Prolog and whatnot, you can only do depth first searching. But what's happened with Oz is that they've actually taken a look at this, and you can see the next generation of Prolog, and you can actually do depth first, breadth first, and best solutions. So yeah, making use of constraint programming is also another way for solving certain issues. You get object-oriented. Many programmers are familiar with the object-oriented paradigm. What's the difference between functional programming and object-oriented programming? It's just a difference of one concept. Just a difference of one single concept. Sorry? No.
Data. All is centered around data.
No. Because functional programming also has data.
State.
Yes. State. Explicit state. So we get like entire groups of people running around saying, I love object-oriented programming, but just understanding the differences of the different concepts. And you see all of them the same. They're all the same, they're just expressed in different ways. So that's the only difference between object-oriented and functional programming, is that a function, or you create an object or an agent, and it's responsible for its own state. That's all. And that state is not meant to impact other parts of the programming language and mess it up. So we can also by having these objects which are responsible for their own state, using these something called a cell. A cell basically is a variable, and it has this data store. And inside the data store, it will have multiple values. And so, if you were at the talk previous to us, we had these permanent collections, right? This is a variation of that. So you could have a reader reading this, which is basically reading this value over here. And then a writer could come along to this cell and then write something into it. And then what this would do is it would point to the new value. But that reader would still be reading this. So you won't get a problem with concurrent reading. And then as soon as the reader stops and then another reader comes along, he will reference that, the newly input thing. So this way you don't break readers and you don't break writers. So this is a way or a technique of introducing state into a functional programming language. And because Oz is a kernel-based language, kernel in the essence that it has very, very simple structures, and then using syntactic sugar, you can make the syntax of the language more easy for a programmer to understand and use. But the actual kernel level of the programming language is very simple and is very easily passed by a computer and translated into machine code. So by using syntactic sugar, you can make it more abbreviated and more easy to work with as a programmer. So maybe at this level, we don't want to have, for example, when we are about to introduce object-oriented programming into this programming language, we don't want to say to you, okay, guys, use a function, but use explicit state. No, we can actually use syntactic sugar and then push it up the scales a bit and then create a syntactic name for that object, which would be a class, you see. So that's how Mozart Oz can support multiple paradigms at once without it being a hodgepodge bag of crazy concepts all just thrown together. Or a programming language which is a shared state concurrent language, thinking, wait, dataflow is a cool idea, let's implement dataflow libraries into this. So there are two ways to basically get expressive power into a programming language. The first is by libraries. All of us are quite familiar with that. But unfortunately, the library approach hits a glass ceiling pretty quickly, because your programming language is only based on maybe one paradigm, which would be maybe shared state concurrency. And shared state concurrency makes use of a couple of concepts, which would be concurrency and state. Sorry, a bit of an obvious one. But so from a concept point of view, there isn't much difference between Erlang and Java. They're both object-oriented concurrency. There's only just different types of concurrency, which would be one is shared state and the other one's message passing. But shared state concurrency is a lot more difficult to reason with when things go wrong, and then you have to change it. It's a lot more difficult to deal with than with message passing. So message passing, you just change a few references to different actors, and you can actually control the concurrency from that point of view. And that's why in this approach I've spoken about, which is this declarative concurrency, making use of ports. Remember, ports allow you to write multiple things. This is a kind of like an actor model. And in every case, those programming languages which try to make the concurrency implicit to the programming, those don't really work. So you actually have to make the concurrency aspect of your programming language, it has to be explicit. Otherwise, you're going to your VM is going to hit all sorts of issues. Okay. So going back into this kernel approach of building a language and supporting different paradigms, you can now introduce logic programming. You can have deterministic, you can have non-deterministic logic programming, and just by using syntactic sugar, you can expose those ways in a very factored way to the programmer. So if your problem has your problem requires a specific technique and a logic that can be solved in a logical way, logic programming paradigm, you just make use of that and you head off and bang away at that problem. Yeah.
Is also strictly evaluated?
You mean statically? Sorry?
And so is it lazy language?
Oh.
The actual implementation of the language, or is it strict and you just get labeled lazy?
Okay. No, Oz is an eager language, but it introduces laziness when you need it. So the idea of this using declarative concurrency is that you introduce concurrency exactly when you need it, but no more. And you introduce laziness exactly when you need it, and no more.
And it's done by you.
Yeah, these three things have to be explicit. Introducing concurrency exactly then and no more. You need to introduce non-determinism exactly at the right points and no more. And then the third one, which was laziness, exactly.
Haskell programmers might disagree with you, but I probably agree.
Yeah, you might, yeah, of course. And that's where we get into the whole language, you know, I use my paradigm, I stick to my paradigm of solving this problem.
Well, the Haskell thing's a little bit more than that, in that the compiler really supports laziness. So everything is lazy, everything works the way to demand given, all function calls, construction, everything.
Yeah, yeah.
Which is very different. That can't even be strapped onto a language in a library or
I agree. It can't be strapped onto a language in a library, but it has to be put into the language. So it has to be explicitly surfaced to the programmer. So from that point of view, it becomes usable. So that's why. So going back to the libraries, the second way to make expressiveness in a language is by using this concept approach, by exposing each of these concepts to the developer at the right time in the right place. So what happens then is that you've got your kitchen cupboard filled with ingredients, and just by understanding concepts, you know which ingredients to pick and choose according to your problem. So, for example, each of these concepts need to be implemented in the correct way. Many programming languages make use of heavyweight threads, or operating system threads. And what happens there is, like, let's say your problem specifically requires that you need to spawn 100,000 threads to be able to solve this problem. If you're using operating system threads, will you do that? You certainly won't. So there you can see that language, that concept badly introduced into your language has caused you as a programmer to find strange ways to try to solve this problem. So your language is now working against you. So that's why in Oz, and also in a language like Erlang, the threading, you can spawn 100,000 of them in under a second and kill them all off in under a second. So those problems that require that degree of flexibility, it allows you to do that. Yeah. Any further questions?
What perspective did you approach this from? Like, what got you into this in the first place? Was it for a project you had to do, or just out of curiosity?
Oh, right. Okay. So, yeah, I was doing some Java programming at companies, and I was just facing with this concurrent problem, and I just thought there has to be a solution to this. There absolutely has to be a solution to it. And I came across Erlang, and then I was kind of shocked. I was like, how did we not learn about this at university? How's it, we should be understanding all of these things. They should be teaching all of this stuff to us. Instead of these big companies like coming in and saying, okay, teach everybody Java. But it just puts everybody in that kind of mindset. You don't know more, and you actually have to go out and study yourself.
I studied parallel programming at uni, and they were doing that Java parallelism, just using this as a typical. Yeah. So that's using shared state concurrency, and so I became a little bit annoyed with the system, and so I just started going off onto my own 3-year streak now, studying Erlang, and then coming across this concepts, techniques, and models of computer programming by Peter Van Rooij and Seth Haridi, and buying that book and then just going through that, and it was just a revelation
to me about there's so many different techniques, much more better ways of solving these problems. So great. I know there was the GPA's implementer. If he'd been in the lecture, it might be good because he could. Hopefully, I could share with him that what Peter van Rooij has found, that those three things which I mentioned over there, they need to be explicit for the programmer to use. And a library level of approach, it doesn't really work in the long run, because you're just going to hit this glass ceiling where all of your libraries make use of shared state concurrency, you see. So it kind of works against you in the long run. So actually the Mozart Oz community, they will be re-implementing the virtual machine. So the virtual machine was implemented growing from about 20 years ago, and then the compilers were not really up to scratch. So a lot of the optimizations for dataflow and whatnot were done by hand. And now every iteration of a compiler that comes out, basically that all those hand optimizations need to be taken away because it's breaking the compiler optimization. So what they've realized is that they need to set up a new base, a new a VM, which is correctly documented and which is done using correct sound principles. So you guys as open source programmers might wish to get involved in that and bootstrap the Mozart Oz language from scratch again and join the community and then get an understanding about these different concepts and how they play with each other. Yeah. So we've got about 10 minutes or so. Any further questions?
So are there any particular requirements for looking after that virtual machine? Is that a good garbage collection or something? To kind of handle all these things, is there some broad picture, or are they just going to take the old one and try to
okay.
smooth over all of the optimization?
Okay, great.
Because I think it would be, if you wanted a Java style language, in the way that Scala kind of took the JVM, that's one thing. But if you already have this thing and there's not something you can...
Okay. So when it comes actually to in some cases the Ozma semantics will not map very well to the JVM, but that is an issue, and that's why you shouldn't really use this for large-scale projects, you see. The point is, this is a proof of concept. This is going to the Scala community who's starting to get more mindshare and say, guys, this is how concurrency
I think people
should be
who've
done.
gone into Scala from Java would now have that realization that sometimes there's a better tool for something.
Yeah.
If you can get it down.
Yeah.
But yeah.
But yeah, I mean, so that's why you specifically, for a dataflow programming language, and dataflow has to be introduced right from the ground level. You can't have shared state and then introduce dataflow on top there. So that's why you do, as you mentioned, with data, the garbage collection is one issue. So dataflow is a good paradigm to be able to do distributed programming. Distributed programming in the sense that it's completely network transparent, except for one small thing, which means you just have to go to a URL and pick up a ticket. And that ticket, what happens is it joins the two processes together. So you're operating in a programming language which is completely network transparent to you. All of the messages that are being sent are folded into the language. You don't have to care about the network. You don't want to care about the network. It's all done with optimized algorithms in the language. At first, when I remember reading, as I was reading this concept CTM, we call it CTM, and I got to that point, and I closed the book. I said, "That's bollocks." Just because I'd been so ingrained into doing my own networking code, I couldn't let the strange black box handle all my networking for me. I closed the book, and for about 4 months or 5 months, I didn't read it again. I thought that's bollocks. But then I went back into it, and I realized actually there is wisdom in this way. So having not to care about networking is a great way. Many techniques that we use to handle errors within networking and distributed programming are in fact incorrect. Even Erlang is getting it wrong. Why? What happens is if there's a network timeout, When I say getting it wrong, I mean also for widely distributed networks. Erlang doesn't function well in a widely distributed internet, on, like, for example, the internet, because for certain reasons. But it's mainly designed for high-performance clusters. Whereas Mozart is, because it's using the dataflow paradigm, you're able to get this programming language running over a WAN. How to correctly handle errors when you're in a distributed environment? You don't have timeouts. You don't say, okay, well, that node over there, it's not responded to my call. That means it's dead. Right? No, it might not be. Could be just like a network fault, temporary timeout. So what happens is you monitor streams. You set up agents which monitor streams of communication. And then what happens, maybe there is a temporary timeout, then what will happen is that monitor will then tell the depending processes saying, okay guys, just act accordingly, we've got a network fault over here, and it might be reestablished later. And so there are 3 different conditions that one can do. So again, this kernel approach to doing to building up a language allows you to expose those critical things to the program, those critical concepts to the programmer to use explicitly, and that stuff which doesn't need to be explicitly dealt with is folded into the language. Programming is hard enough. Why do stuff which can be done implicitly by the language? Yeah. Yeah, I think any further questions? No?
Could you, well, I didn't understand a lot of the talk, to be honest.
Okay.
Could you sort of compare the Oz paradigm for doing things to the Scala actor model and like how it's sort of similar?
Okay, so I believe your mind is still at the point where you're identifying the languages. And by getting more understanding about the paradigms, what the paradigms are, and what consists, what concepts actually create certain paradigms. So a paradigm would maybe object-oriented consists of just two paradigms, which would be object-oriented concurrency consists of 2 paradigms, which is explicit state and concurrency. So your question regarding making a comparison between the actor model and
the paradigm that you described with the ports and...
Okay, so it seems like you've got a more familiarity with the actor model, right? And you want to use that as a reference point. So, okay, by using ports, we can now create agents. An agent consists of 3 things: a port, a stream, and a function. And any message that is put onto that stream gets a function will be called for each message to consume. So everything inside this agent is deterministic. Everything outside of this stream is non-deterministic. So in Erlang, we have something called observable non-determinism. Observable non-determinism basically means if there's a lock, you're going to see something happen. You will see an observable effect from your system. It might throw an error, it might crash, it might do whatever. Yeah, so Java also is an observable non-deterministic language. Mozart is, by making use of this porting mechanism, you have observable non-determinism. Mercury, a programming language, a logic programming language, is observable non-observable determinism. Right. I know, I'm going to go back to that, but I know it's just going to throw everybody off. So just to get back to this, you can create these agents, and these agents can map quite well to the actor model. Because in the actor model, you've got non-deterministic behavior going on inside the actor. Okay, so from that point of view, an agent works quite well. Do you see that mapping there? Yeah. Does that answer your question?
I probably need to read that a bit more.
Okay.
Yeah, I think, yeah, it did to some extent.
All right. Okay. I think we can kill the talk now. So yeah, just go on to the GitHub, take a look for Ozma, and then just work through the paper. It's a great read, and it will certainly expand your attitude towards declarative concurrency and try maybe making use of it. Okay. So thank you very much.